Hello. Today we're going to break down real data from the Euclid telescope, the quick release, one from March 19th, 2025. This is not just a set of beautiful images. It's 63 square degrees of sky, 26 million galaxies, and a catalog of 380,000 objects with morphology and redshift measurements. And even now, these data are reshaping our understanding of how galaxies evolve, collide, and ignite active nuclei. Let's dig in. Quick Release 1 is the first rapid data package following the start of Euclid's main survey, which began in February 2024. The telescope captured 3 deep fields: the northern, the southern, and the field in the constellation Fornix. The total area of observations is 63 square degrees, 7 times larger than the early 2024 release. In just 1 week, Euclid recorded 26 million galaxies, some more than 10.5 billion light-years away. This is a look into an era when the universe was about 3 billion years old. The catalog includes 380,000 galaxies classified by morphology using the Zubat neural network trained on Galaxy Zoo annotations. A multi-wavelength catalog is also available, where Euclid data are cross-matched with SDSS and DC surveys. All materials are open access. And although Q1 is only 0.4% of the future full Euclid catalog of 1.5 billion galaxies, the statistics are already sufficient to test cosmological models. Now let's see what these data reveal. In the well-studied extended growth strip region, the Hubble telescope once showed only a couple thousand galaxies. Euclid, at the same coordinates, detects about 180,000, nearly 90 times more. The Weiss optical channel has a resolution of about 0.3 arcseconds per pixel, and the image depth reaches 24.5 magnitudes. Thanks to this, Euclid clearly reveals spiral structures, elongated elliptical galaxies, and even thin arcs of weak gravitational lensing. The first release reports about 500 new lenses near the Abell 2764 galaxy cluster. Some arcs stretch nearly 18 arcseconds. The mass of the cluster is estimated at roughly 1.2 quadrillion solar masses, with about 85% of that mass being dark matter. In the Fornax field, Euclid also detects extremely faint, low surface brightness structures even near bright stars, thanks to its dynamic range, unmatched by ground-based now through the science. The first paper based on Q1 publishes photometric redshifts for more than 1.2 million galaxies. The measurement accuracy is about 0.03 for redshifts below 1, roughly twice as good as in the DS survey. This accuracy allows us to trace how the structure of the universe and the influence of dark energy evolved from redshift 2 to today. Another important result concerns galaxy mergers and the activity of supermassive black holes. Analysis of nearly 1 million objects shows that the likelihood of triggering an active nucleus after a merger increases by a factor of 3 to 5. For the most powerful active nuclei, brighter than 10 erg per second, mergers are the main trigger in about 70% of cases. Comparison with illustrating simulations shows good agreement, but Euclid finds more rare events. About 200 galaxies contain secondary nuclei, likely candidates for binary supermassive black holes. This matters because the frequency of such events depends on the distribution of dark matter. Without it, mergers would be far rarer. Q1 data also provide the first measurements of weak gravitational lensing. The catalog lists shapes and ellipticities for about 1.5 million galaxies, with a density of 35 objects per square arc-minute. This is an early test of alternative gravity models. At the moment, observations match the lambda CDM model within 2 sigma, but the statistics are still too small for final conclusions. The dark energy parameter W is currently measured with an uncertainty of about 0.3. In the full Euclid release, the uncertainty should drop to about 0.02. The first release also reveals some technical features: cosmic ray noise, which produces up to a couple % of corrupted pixels per night, and stray light contamination in the first. But data processing already compensates for these effects, using deep dark frames and improved point spread function scattering models. And finally, what's next? Q1 is only a small preview dataset. The next major release, DR1, is scheduled for October 2026 and will cover about 2,300 square degrees. It will contain more than 100 million galaxies and a full dark matter map derived from weak lensing. If you want to explore Euclid data yourself, you can download the catalog and open it in TopCat, for example, to plot your own redshift histogram. If you're curious why Euclid found more gravitational lenses than expected, or how merger rates relate to the growth of supermassive black holes, write your questions in the comments. I'll reply with links to the papers. Subscribe if you want more breakdowns like this.